let me turn to this issue of operators and diagonalization. So diagonalization of operators. Now, you might be irritated a little even by the title, diagonalization of operators. Shouldn't you be talking about diagonalization of matrices? Well, there's a way to state what we mean by diagonalizing an operator in such a way that we can talk later about the matrix. So what is the point here? You have an operator, and it's presumably an important operator in your theory. You want to understand this operator better. So you really are faced with a dilemma. How do I get some insight into this operator? Perhaps the simplest thing you could do is to say, okay, let me choose some ideal basis of the vector space such that the operator is as simple as possible in that basis. So that's the origin of this thing. Find a basis in the state space so the operator looks as simple as possible. So you say that you can diagonalize an operator if you can find a basis such that the operator has just diagonal entries. So let me just write it like this. So if you can find a basis in V where the matrix representing the operator is diagonal, the operator is said to be diagonalizable. So to be diagonalizable is just a statement that there is some basis where you look at the matrix representation operator and you find that it takes form as a diagonal. So let's try to understand this conceptually and see what actually is telling us. It tells us actually a lot. Suppose T is diagonal in some basis U1 up to UN. So what does it mean for it to be diagonal? Well, you may remember all these definitions we had about matrix action. If T acting on a UI is supposed to be T, K, I, U, K in some basis, sum over K. You act on UI and you get a lot of U's, and these are the matrix elements of the operator. Now, the fact that this diagonalizable means that in some basis, the U basis, this is diagonal. So Ki in this sum only happens to work out when K is equal to I, and that's one number, and you get back the vector Ui. So this, if it's diagonal in this basis, you have that T on U1 is lambda, a number, times U1. T on U2 is lambda 2 in U2. And T UN equal lambda n UN. So what you learn is that this basis vector, so you learn something that maybe you thought it's tautological, but it's not quite tautological. You learn that if you have a set of basis vectors in which the operator is diagonal, these basis vectors are eigenvectors of the operator. And then you learn something that is quite important, that an operator is diagonalizable if and only if it has a set of eigenvectors that span the space. So the statement is very important. An operator T is diagonalizable if it has a set of eigenvectors that span the space on V. If and only if, this double F, if and only if. So here it's diagonalizable, and we have a basis, and it has a set of, these are eigenvectors. So diagonalizable really means that it has a set of eigenvectors that span the space. On the other hand, if you have the set of eigenvectors that span the space, you have a set of U's that satisfy this, and then you read that, oh yeah, this matrix is diagonal, so it's diagonalizable. So a simple statement, but an important one, because there are examples of matrices that immediately you know you're never going to succeed to diagonalize. So here is one matrix, 0, 0, 1, 0. This matrix has eigenvalues. You do the characteristic equation, lambda squared equals 0. So the only eigenvalue is lambda equals 0. And let's see how many eigenvectors you would have for lambda equals 0. Well, you would have, if this is t on some vector a, b must be equal to 0. So this is 0, 1, 0, 0 on a, b, which is b and 0 must be 0. So b is equal to 0. So the only eigenvector here, I'll just write it here and then move to the other side. The only eigenvector for lambda equals 0, the only eigenvector is with b equals 0. So it's 1, 0. One eigenvector only, no more eigenvectors. By this theorem, or by this claim, you know it's a two-dimensional vector space. You just can't diagonalize this matrix. It's impossible. Can't be done.